And somehow I missed the intro 30 seconds and we are magically live. Welcome to Kubefirst Unhinged. That's the right way to start the show. So hello, everybody. I am John Dietz. I'm here today with my good friend, John Platt. John, would you like to introduce yourself for a second?
Yeah, hey John, thanks for having me. So I'm the CTO of StormForge, and we have a machine learning platform to optimize resources on Kubernetes. Delighted to be here today to talk about various sort of autoscaling projects on Kubernetes, which is obviously closely related to what we do, and essentially if you want to run Kubernetes in a reliable, efficient manner.
Thank you so much for that. And where are you calling in from today, John?
Oh, I'm near you. I'm based out of Arlington, Virginia, so just outside Washington, D.C.
Yeah, DC representing today on Kubefirst Live. I love it. I love it. So obviously to our audience, everybody's wondering where Fred is today. And that's right. That means it's another edition of Kubefirst Unhinged, where I get the opportunity to miserably fail at orchestrating a live stream live in front of our viewership. So it's a pleasure to have everybody joining us today. Yeah, I met John quite a bit ago, and we've been talking on and off about his StormForge product. Really interesting product for resource monitoring, keeping costs down, auto scaling, and John, if we can. We've got some GitOps catalog stuff to get to later on, but I was hoping that we could just kind of jump right into StormForge a little bit, and you could share with our audience a little bit about your product. And also, I was hoping that we could get into some auto scaling techniques and just kind of give us a view of your world that you live in.
Yeah, perfect. You want to bring up the slides?
I'd be happy to.
Let's see. Great. And please, everyone, jump in with questions. John, jump in with questions. It's always way more fun if it's interactive. To sort of frame it out, there's 3 dimensions of autoscaling on Kubernetes. 2 of them, I'm sure people are familiar with from VMs. Horizontal autoscaling, which is how you add and remove replicas, either containers, pods, VMs, as the load on an application goes up and down. There's vertical autoscaling, which is how do you actually size whatever's running your application. It could be sizing the container on Kubernetes using requests and limits. It could be picking, do I need a T2 medium, T2 2x large? Like, what do I actually need if I'm running on VMs? So horizontal and vertical are sort of well understood, established, etc. And then unique to Kubernetes is cluster autoscaling. At least unique to people who are moving from VMs to containers. And the idea is if you're running lots of containers on nodes, you need to find a way to provision those nodes and get the right nodes as the sort of traffic and the workloads running your cluster go up and down. So there's 3 dimensions, and then there's a variety of different projects. There's a variety of different projects out there for each. I'm sure most people are familiar with the HPA. So this is built into Kubernetes. It will add or remove replicas based on initially CPU utilization. Now with the V2 of the HPA, there's a much wider variety of things you can scale on, custom metrics, external metrics, etc. And then for people who want to get a little fancier, there's something called CADA, the Kubernetes Event-Driven Autoscaler, which makes it much easier to scale on things which are not sort of built-in metrics like CPU utilization. For cluster autoscaling, there's the cluster autoscaler, which is built into Kubernetes. We'll talk a little bit about that today. And then we'll actually do a demo of a new project open source by AWS a few years ago. Called Carpenter, which we think is amazing. And then finally, on the vertical side, there's the vertical pod autoscaler built into Kubernetes, not as heavily used as a lot of the other tools. And then StormForge, which uses machine learning plus various other sort of refinements to try and make that a little bit easier to adopt. And then the goal is to actually find an automatic way to set resources for applications and run them in a way that is efficient without compromising reliability.
You're right on. And just so that I'm sure I'm understanding the world right, vertical pod autoscaling versus horizontal pod autoscaling. This is basically when we're talking vertical, we're talking about how much resources are allocated to individual pods, and then horizontal is how many pods replicas there are. Is that a sane way to think about things?
Perfect. Absolutely
Awesome.
perfect.
Okay.
So let's dive in. I'm going to start with the cluster autoscaler, or cluster autoscaling in general, and that's because that's typically where people start when they start running workloads in Kubernetes in production. So this is a simple example of how the cluster autoscaler works. The point of the cluster autoscaler is to add nodes to the cluster as needed, and then remove them when they're not needed. And the way that the cluster autoscaler does that, and all my examples here will be AWS, use AWS language. It works very similarly on other cloud providers. And I think the cluster autoscaler has 20 to 30 cloud providers which support it now. So the way it works is it's constantly watching for pending pods. So you go to schedule new pods, and you start, the scheduler will place them on nodes. Eventually you'll run out of capacity and those pods will be unschedulable. And then that's the signal that cluster autoscaler uses to be like, okay, we need to add more capacity. So the cluster autoscaler is going to see an unschedulable pod, decide it needs a new node, and then it will call through to the autoscaling groups running in your cloud provider, which will then spin up a new VM. And once you have the new VM, the scheduler built into Kubernetes will place the pod on that machine. The way I've shown it here is you have multiple autoscaling groups. So if you want to use a variety of instance sizes, imagine you have imagine you have some workloads which need special hardware like GPUs, or you have some which are extremely memory intensive and need a specific shape node, etc. Yeah. You have to create an autoscaling group for each of these. And then you have to, in your application, decide, okay, this workload needs to run on that node. And you can use the various sort of scheduling methods built into Kubernetes, node selectors, taints and tolerations, etc., to place it on a node. And it works, but it can get a little bit clunky at scale. And there's a little bit of a overhead creating and managing all of these autoscaling groups. It also gets a little complicated if you create a pod which could run on a variety of autoscaling groups. There's something called an expander, which will decide, okay, of these 5 options, which one do I pick? And it's very configurable, etc., but it can get a little bit complex.
Yeah.
So that's how it's going to add nodes. And then that's great, but eventually imagine you're running some sort of workload which is very heavy during the day. You add capacity, you get to the end of the day. Imagine you're a bank, you do most of your business 9 to 5. So you get to the end of the day and you're like, okay, well, now I want to remove these nodes. And then the cluster autoscaler also has to take care of that. And the way that that works is it looks at each individual node. So I've got a simple picture here. Each of these blue boxes is a node. Each of these white boxes is a pod running on that node. All of the pods, all of the nodes are the same size, and you can fit 12 pods to a node. And then the way the cluster autoscaler works is it's going to look at each individual node, and then it has something called a setting you can pass to the cluster autoscaler called the scale down utilization threshold. By default, it's 50%. So it's going to go in, it's going to look at the allocated resources, the requests which are actually set on that node, and see if they are above or below 50%, or whatever you've configured this to be.
Okay.
And anything which is below it, it'll shut that node down. So I've drawn the line on each of the nodes, and you can see there's three where it's below 50%, and these would be candidates to be scaled down. It also provides the ability, it's very, very configurable. So you can set a wide variety of different flags to control the scale down behavior. You can also annotate nodes. So you can annotate nodes to say, do not disable, scale down disabled. So for example, imagine you had something which was running a metrics agent. At no point do you ever want whatever Prometheus agent is shipping data to your monitoring solution, do you ever want that scaled down? So you might put that down, you might put that on a specific node and then annotate it so it would never be removed.
Interesting.
And you can do the same with pods.
And
so,
sorry, can I just ask real quick, John? When thinking about cluster autoscalers, I'm trying to think of the signature of the type of cluster where that's appropriate. While you were giving that description, you were describing the bank, and that's a perfect scenario. Bank has a very typical business hour flow about it, and there are just a lot less users in a certain time of day than another time of day, and that makes a lot of good sense to me. And that just sparks to me like, well, there's also like CI, right? Perhaps you have a dedicated CI server, and that has heavy fluctuation of job requirements and needs while developers are clocked in. And then in the wee hours of the morning, maybe there's one person doing some work, and they don't need that much horsepower. Are there other signatures? Is there ever a type of cluster that, in your opinion, doesn't need an autoscaler?
There probably is, but I don't think it's. There probably is, but it's probably a little bit more ephemeral, just used for development, etc.
Yeah.
Or maybe some applications are just extremely static.
Yeah.
Or imagine a case where you're running bare metal GPU servers and you've bought them, you've racked them, you're not getting any more. But if you're running in the cloud and you have any sort of variability in your workload, it's common. And these cluster autoscaling solutions are just ubiquitous. They're everywhere because most people have clusters where the load changes. And if you're not using it, you don't want to pay for it, especially in the cloud.
Yep. Very neat. Thank you.
So I have a simple animation just to show what will happen. So there's two nodes which are candidates to be scaled down. Before actually scaling down a node, Cluster Autoscaler will check that the workloads which are actually running on those nodes can be rescheduled on existing nodes. Because the last thing you want to do is scale down a lot of nodes, realize that you don't have enough capacity, and then have to spin a node back up, because that leads to just poor performance, potential short outages, and thrashing in the cluster. So it will check, and then it will scale them down. And what you will end up will be this. And you can see that this node would still be below the threshold to be removed, but it has the annotation, so it will stay. And Cluster Autoscaler is very conservative when it comes to scaling down nodes. So by default, and again, it's all configurable, it removes one node at a time, and it waits 10 minutes between nodes. So if you have a big spike in the day and you need to remove 50 nodes, it could take several hours. Again, you can configure it, but we've seen issues with this in the past where there's just like a very long cooldown period and you have underutilized nodes, which you're paying for a fairly long time.
Gotcha. And just for my own curiosity, like if it's in the middle of a downscaling process, and suddenly traffic starts to increase and demand starts to increase, is it safe to assume that it will recognize that and stop its continuation of the scale down?
Yeah, 100%. Great question. So the node has to meet that threshold of less than 50% for 10 continuous minutes. So if you were to be sitting there for 8 minutes underutilized and then you had a spike and a new pod on it, it would reset the clock and you would keep the node. And again, it's just Cluster Autoscaler is very conservative, scaling down nodes. So yeah, it would short circuit that.
Right on. And just one last nerdy question. In the old days, or even nowadays, if you needed to proactively manually remove a node for some reason, you have to taint that node. You have to evict all of the pods yourself. Make sure that everything has safely been evicted and rescheduled on other pods. And then that node's easy to remove. All that type of stuff is all just automatically orchestrated through the autoscaler techniques. 100%.
I actually think, I wasn't planning to highlight that, but I think we'll probably see that later when I do a short demo of Carpenter.
Neat. Very cool. Very cool.
So that's nice. So it brings us to Carpenter. So Cluster Autoscaler has been around for 7, 8, 9 years, since very early in the Kubernetes project. Carpenter was created and released by AWS, I want to say 3 years ago now. They open sourced it from the beginning, and it was always designed to work with a variety of cloud providers, just like the Cluster Autoscaler. AWS was the first. And then Azure released a provider which provides support for Carpenter at KubeCon last year in Chicago. And it's got a lot of adoption. What we see is a lot of sort of greenfield projects now in AWS use Carpenter rather than the Cluster Autoscaler. And there's a few different reasons, and I'll sort of drill into a few of them. So the first is Carpenter is much quicker about adding and removing nodes. And we can get into a little bit about why and how. But that means, imagine you're scaling up. The last thing you want to do is, if you have pods which are unschedulable and pending, you want to get them scheduled as fast as possible. So getting those nodes created quickly is key. Second, it eliminates this idea of node groups. So I showed those multiple autoscaling groups before. It completely eliminates the autoscaling groups. And what that allows is, they call it groupless node provisioning. It allows a lot more flexibility as nodes are scheduled. So as I mentioned before, it's open source, and it also provides ongoing consolidation, which I'll talk about a little bit more in a moment, which is a sort of smarter, more efficient way to do that node removal than what the cluster autoscaler does.
Real quick, John, this is actually super interesting to me because I'm passively familiar with Carpenter. I hear great things about it in AWS regularly. I know of it as an AWS product, frankly, kind of akin to the AWS Ingress controller, as an example. Mm-hmm. And whenever there's a technology that a cloud produces, my instinct is always, whoa, watch out for lock-in, et cetera, et cetera. But it sounds like the Carpenter architecture is set up with a provider paradigm. Any cloud provider would be able to produce its own Carpenter implementation for that cloud implementation. So it is being implemented in a very open way where all the clouds could play with the standard.
100%, and it was donated to the CNCF last year. Fantastic. So it's not even managed by AWS directly anymore.
That's awesome.
Yeah,
appreciate that.
Yeah. It's and you said you've heard good things. It's a fantastic project. So a little bit about how it works and how it can get a little bit of extra, how it can be more flexible and a little bit quicker than the cluster autoscaler. So this is a diagram, same diagram as before, just with one autoscaling group. You have pending pods, unschedulable pods. The cluster autoscaler sends a message to the autoscaling group to say scale up, which talks to the EC2 API and creates a node. So with Carpenter, that step is eliminated, and Carpenter runs in the cluster and it talks to the EC2 API directly. So you get a few major benefits out of that. So first, you avoid one of the hops. You don't have to talk to the autoscaling group and then wait for it to talk to the EC2 API. So what people typically find is it's typically 45 to 60 seconds, significantly faster to start a node, which is fantastic. The second is that so if you were to do the cluster autoscaler approach with autoscaling groups, you have to create something called a launch template, which is the template for the autoscaling group to create new nodes. You would need to manage that in Terraform, and then you would have to then pass that sort of the name of that launch template. I think that's how it works. I can't remember the details, to the cluster autoscaler to know which autoscaling groups it should talk to. You would pass the name of the autoscaling group, which would contain the launch template. So this creates an awkward break between what you can actually manage inside Kubernetes and what you have to manage in other sort of infrastructure tooling. Carpenter creates launch templates ephemerally. So when it decides the right node to launch, it will create a launch template, submit it, launch the EC2, and then it will go away. So what this means is you remove a lot of the overhead and you consolidate all of the configuration inside Kubernetes, which makes it a much better user experience. It also means you can spin up a wild array of different node types without the overhead of creating the autoscaling groups, managing them, etc. So you get much more speed and flexibility by talking directly to the EC2 API.
Quick question for you. So I'm just kind of thinking through applying this to my own infrastructure. And one of the things that jumps to mind is the Terraform that we use to create that cluster in the first place. And we're specifying the number of nodes that are in, say, a default node group. Then we add to that cluster Carpenter, and Carpenter is capable of scaling that cluster to have less or more nodes than were defined in your IAC. What is the appropriate technique for an IAC created Kubernetes cluster to implement auto scaling in a way where, like, the next time you run a plan, it doesn't try to reduce that back down to its initial settings? I don't mean to put you on the spot with that. It's just a curiosity.
You mean updating a cluster?
Yeah.
It depends what you were updating in the cluster, but I suspect if Carpenter is running in the cluster and it's managing the nodes, you would just have no issues.
Gotcha. Okay.
I suspect. I would need to drill into the details more to be sure, but we've not run into issues with running into any. We use Carpenter ourselves. We use actually a lot of the tools I showed at the beginning. We use Kata to scale out our machine learning backend. We have like a task queue with various machine learning tasks in it, and we scale up the number of workers in a pool based on the length of that queue. We use Carpenter to provision nodes and consolidate to accommodate those bursts on the machine learning because it's very compute intensive. And then we dog food our own product, and we use StormForge to size the workload. So we use a lot of these, and we've not had this issue with Carpenter.
Very neat. Okay.
So that's how Carpenter is going to add nodes. And then the question is, what about removing nodes? And this is where Carpenter's consolidation is just a little bit smarter, and it drives extra efficiency. This is just the exact same scenario I showed before for the cluster autoscaler. It would consolidate it down to here. But what you'll notice is there's 1, 2, 3, 4, 5, 6, 7, 8 pods here. And there's enough space on the other nodes that you could still remove another node and still schedule all of these workloads. And the key difference here is Carpenter's going to look across the entire set of nodes and reschedule not by looking at individual nodes, but the whole cluster. And with that scale down target utilization of 50%, imagine you have 100 nodes and you have 50% allocated on every node. Cluster autoscaler will say, okay, every node's fine. Let's just accept the 50% waste.
Yep.
Carpenter will say we could remove 50% of these nodes and still schedule everything. So by actually looking at it on an ongoing basis, it can drive significantly more efficiencies. And I've done the example to spell it out, and you can see you can still fit all the pods without running out of resources on the nodes. So it's high level. I think slides, it's nice, but it only goes so far. I have a demo, and please jump in anytime.
Sweet, thank you.
All right, so I have a cluster.
Sorry, John, can we get you to, if you're changing?
Oh, yeah, you're totally right, totally right. I'm on the wrong screen.
Thank you.
All right, here we go. Nice catch. Where am I? Here we go.
Somewhere around here, there's some elevator music I could play.
There we go. You can see it now.
We are looking
It would have
good.
been
Thank you, John.
the perfect time for a sound effect. Hey, so this is a cluster I'm running on EKS. You can see we have Carpenter running in the Kubesystem namespace. This is an example of you create a node to run Carpenter, and Carpenter manages the other nodes in the cluster. So if I show it, there should be one node. There's no workloads running. If I do, there's nothing running outside Kubesystem yet. And then have you heard of the EKS node viewer?
No.
It's a small project put out by the Carpenter team. It makes for an amazing demo. So I'm going to run it with the different resources, CPU, memory, pods, and it's going to show me all of the nodes running in my cluster. And to start
really
with,
neat.
It's amazing. I love it. And to start with, it's just the node which is running all of the Kubesystem workloads. And we obtain its toleration so that nothing else will get scheduled there. And then all the other workloads will just drive the new nodes, which will get provisioned.
That's awesome. Hey, John, can I bother you to increase your font size by 2 ticks?
Is that better?
One more. Thank you so much. Yeah.
How about this?
It's a little small.
let's see if the EKS node viewer will respond. That's bigger, I think.
Let's play with it. Let's go.
There we go. All right. So you asked before about how it works with different cloud providers. So there's been two things which have been created when Carpenter was installed on this cluster: node claims and node pools. If I look at, sorry, 1 second. What am I'm missing something. Oh, up here. There we go. Wrong one. So you can see here there was an EC2, so an AWS specific Carpenter object. And this is where you put in things like what AMI do I want to use, etc. Anything which is cloud provider specific goes in here. And each of the different providers, I'm sure Azure has one similar to this. This is where you put the what VPC to launch things in, etc. You see the subnets here. This is the cloud provider specific part of the Carpenter sort of objects. And then you also create node pools. So the node pool, so the way Carpenter gets its flexibility is rather than have an auto-scaling group where you hard code the instance type, instead you just give it requirements. You say, okay, I'm happy to run on anything which meets these requirements. And it's very flexible. So you can say what architecture, you can say what OS, you can say category type. So you could have Spot in here, and then it will use on Spot when available, when it's cheaper. Otherwise, it will use on demand. And then here you can set the instance category. So CM&R, compute intensive, general purpose, and memory intensive. So you define things in the requirements. You create workloads, and then Carpenter does all the logic to decide, okay, what's the right node to run this workload? So I have a few workloads here. I have one which is CPU intensive. So you can see it's just a pause container, and it has a 1-to-1 ratio roughly of CPU to memory.
Yep.
And then I have one for memory where it's the same amount of CPU, but 8 times, or the same amount of CPU, but 8 times the memory. And the point here is that when you're running a wide variety of workloads in a cluster, they have different requirements, etc. It breaks the sort of one size fits all that goes with hard coding instance types in auto-scaling groups. So let me create those. And then if I go over, perfect. We see a node getting spun up. And what's happening is those pods were created, they were unschedulable. Carpenter saw that, and now it's creating a node. And it's decided that when you have one CPU heavy node, or one CPU heavy workload, and one memory heavy workload, the right shaped node, shocking no one, is a general purpose one, which is kind of a mix of the two.
Yep. Very neat. Very neat.
And this is going to take, there we go. So we can see it come up. So, okay, workloads aren't static. Let's scale them up. So we can scale up the CPU intensive one and add 10 replicas. And you can see what happens is the node very quickly maxes out on CPU, and then a new node is created. And the new node is created, you can see two things. First, you can see that it's a C, so that's compute intensive. Now that the mix of workloads is skewing more towards CPU, Carpenter notices that and will create CPU nodes of a similar shape. And you can see now that we have way more replicas, rather than have a medium, it's a extra large. So it's 4 times the size of the one before. And I think you get the general idea. It will do this on an ongoing basis. For example, if I go in and I now do the same thing for memory, what I strongly suspect is going to happen, though I could be wrong, is it'll realize that, okay, this medium now, this general purpose medium isn't useful. I need way more memory. So it's probably going to, my suspicion is it's going to reschedule those pods on an R and then remove the M. And it will just be constantly doing this on an ongoing basis in the cluster.
That's really neat.
It's amazing. Yeah,
The
yeah, it's great.
visualizer was great too.
The visualizer is the best. It just makes for like such a compelling demo. If I was describing this and you couldn't see it, it would be nowhere near the same.
Yeah, it's a lot of words and a lot of trust, right?
Yeah, exactly. So I think you get the idea. How Carpenter works and how Cluster Autoscaler works, watching the unschedulable pods, creating the nodes as needed, the logic to spin them down, why you need to actually do that on an ongoing basis and consolidate on an ongoing basis. Carpenter has a whole bunch of other really nice features because it's managing the nodes directly. You can actually put changes to the kube config. So you can patch the kube config on the nodes if you need to do something custom. Not the kubelet config. It's amazing for spot instances. There we go. As predicted. Oh, I was about to say as predicted, the M got spun down, but it spun up a new one. Maybe that's a smaller one. I'm not totally sure. I can't remember what it was before. But you get the idea. And then the other big thing, which I probably don't have time to demo, is spot instances. So Carpenter is fantastic for spot instances for a few reasons. First, it has a bunch of nice features to catch the spot interruption notices early, which means you get told, I think AWS gives you a 2-minute warning. Yeah. It will catch that and start rescheduling those workloads immediately. And because it's able to launch nodes so rapidly, typically under 60 seconds, you can typically have those workloads rescheduled before that spot instance is removed. So it's amazing for spot instances as well. So that's Carpenter. But while people typically adopt Carpenter for cost reasons, the problem they run into is the way that Carpenter is making decisions is, one second, let me switch back to my slides. The way that Carpenter is making decisions is saying, okay, what are the requested resources on that node or on the cluster, and what nodes do I need to do that? But that only works if you have actually set your resource requests appropriately. If they're massively over-provisioned, then your nodes are still going to be really inefficient because you're just bin packing. You're efficiently bin packing lots of empty boxes, and it's just kind of a waste of time. And the dirty secret is most people use almost none of the resources they request. So this was an amazing survey done by Datadog. They did it a few years ago, and then they updated it last November. 50% of workloads use less than 25% of the resources they request, which means no matter how well you bin pack, it's just kind of a waste of time. Not a waste of time, but it's just there's only so much efficiency you can squeeze out of the cluster if you're just focused on the nodes.
Right.
And the question is often why. And the reason why it's so efficient is because it's really hard to set requests appropriately on clusters. And we see this all the time working with customers. Everyone goes through the same journey. First, they don't bother setting requests, and then they go down, and that's unacceptable. Then they're like, okay, we should set them. What do we set them to? And they use a one-size-fits-all approach, or they use, if they get fancy, they t-shirt size. But if you ask a developer, what t-shirt size do you need? Everyone says XL. No one's like, give me a small, because no one wants their workload to go down. So they end up with massive over-provisioning, and it becomes expensive. And eventually it becomes so expensive, people decide that they're going to try and fix this manually. So they go in and they start looking at dashboards, building tooling, etc. And that might work if you have a handful of workloads. But once you get to scale, it becomes really grueling to manage. You want to have, we have customers with tens of thousands of workloads. To get developers to look at each of those once a week would be just a massive amount of engineering time and just overhead managing the process. So we've seen many people try, we've seen no one succeed with this manual approach. And that's where StormForge comes in. Our product, we have machine learning and automation to solve this problem. And it's a problem which is perfect for machine learning for a few reasons. First, all of the data you need to sort of solve this problem is pouring out of the Kubernetes cluster. There's metrics endpoints built into various components. You can watch the API server to discover workloads. It's extremely one-click install, and you can get everything. And then you can get all of the recommendations. This workload needs these requests. And then it's not just about access to the data, but how do you automate your insights? And Kubernetes has all of the APIs to patch, update on an ongoing basis. So it's a problem perfect for machine learning. And I can go into a demo. What you end up seeing is something like this. So it's a one-click install, or John's going to show how you could do it with the Kubefirst platform in a second. So you install, we automatically pull all of the workloads, we discover all the workers in your cluster, we pull all the data out, we send it to our machine learning backend. The machine learning starts cranking, starts making recommendations, and you get a summary like this. And it's trying to highlight current state, what you actually need, and what you could potentially save. So this shows the current requests, what we recommend with dollar estimates, and then the savings. And we break it out by what is waste being eliminated, and then what is being reallocated to under-provisioned workloads, which are always much less common than over-provisioned workloads, but much more problematic, because it's better to be reliable and expensive than under-provisioned and go down. So you can see what the value is. You can click in. You can see we have the usual hierarchy: cluster, namespace, workload. And then when you get in, you can see what our recommendations look like. So this is a sandbox app. You can see the different percentiles of usage over time. And then you can see what our recommendations are. And you can see that we're basically surfing on the peaks, which is what you want to do, because again, you don't want to run out of resources. The agent you install is read-only, and typically what happens is people install it, they wait a few weeks, they see what they could save, they learn to trust the recommendations, and then the question is, okay, how do I actually take this to production? And the way we work is we have patches. We're compatible with the HPA, which is one of the big blockers people have when using the VPA. We can layer on top, so we can optimize and vertically size workloads alongside the HPA. And the way we do that is we patch the target utilization for the HPA alongside the resources for the workload. So we create patches, and then you have two options. You can either install a second component which has write access to the cluster and will automatically patch on an ongoing basis, or you can pull the patches from our API and you can do whatever you like with them. You can check them into GitOps, you can apply them yourself. People sometimes have slightly more complex promotion processes. You want to patch a perf test workload and test it first, like stuff like that. But you have an easy path to automatically apply, plus the flexibility to do whatever you like. And then the final question before actually going and sort of turning on the automatic application and applying these to production is, how do I actually control the machine learning and get it to do what I want? So we have a variety of different configuration options. And we don't expect anyone to come to the UI and make changes. This is done just for demo purposes. It's all done declaratively in the cluster. You can annotate workloads, namespaces. You can set defaults at the cluster level. But the main things people are actually setting is, first of all, how often and at what time of day do I want to deploy recommendations? Typically, people do it once a day, which minimizes disruption, and they do it overnight. You can set the optimization goal, which is going to tell the machine learning, okay, this is a workload which is a little bit more resilient. You can be more aggressive and target savings. This one is a little bit more finicky, be more conservative. And this lets them control, do I want to really squeeze everything I can out of this, or do I want to just eliminate the waste but still be a little bit more conservative? And then you can control different policies for requests and limits, how people use limits. There's a little bit of a holy war. We have thoughts, but people will do what they want for their application, so we support everything. Yep. And then we let you control minimums and maximums. You can set guardrails. Don't go below this, above that, etc. Again, the goal is to let people constrain the machine learning so that they can make sure it does what they want and expect. And that's it. The whole point is to make it as simple as possible. There's enough tools out there. People don't want to take on unnecessary complexity. Install, we discover everything, show the potential savings, provide the ability to patch and sort of control the machine learning. And then typically people save 40 to 60%. And that's partly because the machine learning is great, but it's mostly because over provisioning is so ridiculously ubiquitous that there's just so many low-hanging fruit to be picked. Yeah. It's
really neat. That's really neat.
And that was my demo. And I think you wanted John to show just a little bit more about the installation process.
Yeah. If you're all wrapped up, John, I'm going to present the GitOps catalog variation of installation. Let me go over to screen 2 here. And here we have a, excuse me. Here we have a Kubefirst install. This is our latest version 2.4.8. And these are the core applications that come with the platform that are ingressed. There's also the GitOps catalog, which features a whole bunch of high value applications that you can add to your Kubefirst platform after you produce your Kubernetes control plane cluster. And so here we have the StormForge agent, which we can install just with a simple click. Now for the values here, we have two of these are actually not secrets. These first two, if I hit the eyeballs here, this is just two values that need to end up in a secret so that you can leverage Vault as your secrets manager. When you do an installation, if you walk through the StormForge docs, they'll basically request you to do an install. They give you in their user interface here, which I can bring up here. When you go to create your first cluster, we want you to name your cluster the same name that you named your cluster when you provisioned that cluster in Kubefirst. That allows us to make sure that the name that shows up in StormForge matches the name that's ubiquitously throughout the rest of the Kubefirst platform. So that is an important detail to make sure you get right. Don't call this like my first, StormForge cluster or something like that, or it'll be misaligned. So my particular cluster is named MGMT. When I hit continue here, StormForge is going to give me a couple values that I need to use for the installation process. So I'm going to take this client ID and drop it back here in the client ID field. And I'm going to take this secret, and I'm not going to include that last space, and drop that in here. And before I hit add, in fact, God, I'm a little bit concerned that I was logged out, and I was logged out. So I had to do a quick refresh. Forgive me. Give me 1 second. I have to re-enter those fields. And let's go back to the GitOps catalog. Second verse is the same as the first. We're going to do install. And if I grab my StormForge URL one more time, I heard a rumor. It's important to make sure that you include that final slash, and I trust the rumor. And then again, back to the user interface here, we're going to grab this client ID and this secret here without that trailing space. And over here in Argo CD, before I hit go, do the same login, song, and dance. There we go. We're logged back in, single sign-on. And in settings under repositories, by default, Argo CD only has a single repository that we set up for you that's basically just for all of your interactions with our GitOps repository. Now, the StormForge Helm chart is an OCI Helm chart. So it's a little bit different. It means in Argo CD, you're going to have to register the OCI repository so that you can pull the Helm chart from their OCI repo. But we have that automatically wired into the Kubefirst repo, or the GitOps catalog. So when I hit add here, what this is going to do, the first thing that it's going to do, this does no operations directly against your Kubernetes cluster at all. We're only interacting with a GitOps Git repository. So right now what we're doing, in fact, I think I can show it on screen. If we go to the GitOps repo, we should have a commit as of a second ago. Yeah, right now. And if we click this commit, so these are the files that we add to your GitOps repository when you do a StormForge agent installation. And it's important to note the sync waves as well. So we have a top level application that says that all the StormForge components are going to be at registry clusters management components StormForge agent. And that's because of the cluster that I chose That's why it's going to the management cluster. And then this is the application kind. It's a StormForge agent. Why do I keep tripping up on StormForge? I'm saying it's terrible. StormForge agent. And this is the important detail to allow it to work with Vault. We set manage all secret to false, and that allows us to get the secret into the cluster some other way. That other way that we do it is through this external secret right here. The GitOps catalog is automatically taking those secrets that we entered when we did the install, adding them to HashiCorp Vault, producing the external secret to be able to pull that back out of Vault, put it in the namespace so that the StormForge agent can leverage it.
If Fred was there, he'd have a sound effect.
I know, he sure would. He sure would. And then down here, this is the one last detail. There is a OCI registry StormForge Argo CD secret. And this is technically a Kubernetes secret. However, none of the values in here are sensitive. So we're okay just putting it directly in the GitOps repository. These are basically like, this value is true. This is the server endpoint. This basically says that it's OCI. And this is how you get to the chart. So none of those are sensitive values. We're okay putting these directly in the Git repository, but wanted to call that out. And then that's basically the whole thing. And I think at this point, if we went to Argo CD applications to the registry, there should be a StormForge. There it is. And if we drop in, these are the three components that we were just looking at. It's the external secret that produced the StormForge agent secret, and then the application itself. The application, if you take a look, it's in a healthy state. And because of that, when we go back to the user interface here and say, yeah, continue, you can verify the installation. And then in a couple seconds, it'll say, hey, we got you covered. We're going to start monitoring your cluster. Right now, my cluster that I've installed this agent to is feeding that metadata up to the SaaS product. And then in just a matter of moments, we would get it's app.stormforge, right?
Yep.
So I have another cluster. We were just looking at the free GitOps Magic cluster. This is the GitOps Magic cluster. It's a different cluster. This one I set up yesterday, and it's been running for a little bit. So you can see that we've got all of your usual suspects of namespaces. They're all getting that nice, rich metadata. And if I were to follow the docs that StormForge puts forward, I would basically just let this marinate for like maybe a week or so. Let it get a real sense of your workloads of, certainly with things like Atlantis, like right now, if you were to look up at the Atlantis, it's going to say them grossly over provisioned, but this is also a demo stack and we're not using Atlantis. So you want to be using your system in your typical way, allow that typical use to have an opportunity to marinate with this ecosystem. And then it's time to start acting on the intelligence that it's built up over that period. So that was really all I wanted to show about that. And John, I don't know. I think that was a pretty successful demo. You taught us
I thought it was a great demo. The install was really slick.
Oh, thank you so much. Yeah, and everybody that already has a Kubefirst platform in their production environments or whatever, just because we added this new StormForge app to our GitOps catalog literally last night, that does not mean that it's not available to you today, even without an install. So anybody that goes to their GitOps catalog, if you want to start messing around with StormForge, you can conduct that install the same way that I just did on screen. And you, John, anytime you guys want a demo, if you want a easily reproducible Kubernetes platform, you can add StormForge agent just as easily. So, but appreciate all the overview of how the different auto scaling disciplines work and the all the nuanced details about the technologies that are in play was super eye-opening to me. And the StormForge product is a really good product. It was easy to set up. It's even easier with our GitOps catalog. Just boop, 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 and you've got it taken care of. Argo CD. It's GitOps ready. It's ready to go. So I hope our users experiment with it. And if anybody has any problems with it, hit my boy John up. And if anybody has any problems with anything about it running on the Kubefirst platform at all, obviously hop in our community. We will make sure that you are successful with it. So
yeah, and if people do want to hit me up, you can find me on LinkedIn. I think one of the links was shared earlier, or email me, john@stormforge.io. Any questions, feedback, anything, always around. Just would love to hear from people.
Right on. Well, John, I appreciate you putting up with me trying my very best, Fred. I was clumsy in here. I don't know where any of these buttons are. The guy's so good. And you never really stop to appreciate how good your DevRel is until you're stuck doing the job yourself. And for your patience while I figure it out on the fly, I thank you. And I thank you for hopping on our show today and enlightening our audience on autoscaling. It was really, really a great demo today.
Yeah, delighted. Happy to be here. It was super fun. Thanks for having me.
Yeah, of course. And John, I am ill prepared. We have a very, very serious requirement on the Kubefirst live show where at the end of every show, we like to end with a dad computer joke. So I am not prepared for that. I'm going to be super.
You're providing the joke, right?
Yeah, we're
I thought you wanted me to pull one up just
I'll give
on
you
the fly. I was like, I might be a Hey, you're okay. Give me a joke then.
Okay, here we go. What did the teacher say to the Disney insect learning to use a computer mouse?
What did they say?
They said, Jiminy, click it. That's fun times. That's fun. I don't even have the badum-ching ready. Fred will have to give me 1,000 lashes when he gets back. But John, it's a pleasure having you on the show today. Thank you so much for joining us. And everybody else, we'll see you in 2 weeks when we have Git Guardian coming on the show. So thank you for joining us today. John, any last words before we wrap up?
No, this was great.
All right. Thank you guys so much. We'll see you soon.